In this lesson, we're going to quickly go over a really simple concept called maximum power transfer. So first, let's go ahead and draw a really pretty simple circuit. I don't know if I can do it without messing it up there. Let's see. We've got a voltage source that we'll call VTH. It's a Thevenin source. And then with that, we have our Thevenin impedance, ZTH. And that's going to be attached to some load that we'll call Z sub L. And all we're really interested in is how do we get the maximum power to the load. And the reason it's a little bit tricky is because as you sort of mess with the ratio of ZTH and ZL, right, you're going to mess with the voltages and currents. And so you're looking for a sweet spot where, as voltage goes up into ZL, that means the current goes down, right? And then vice versa. As the voltage goes down, the current is going to go up. And so you want to find that sweet spot where you're getting the maximum value of the power. And it turns out it's pretty easy. The relationship there is that ZL should be the complex conjugate of ZTH, or our Thevenin impedance. And then once we've matched that correctly, our power, our maximum power delivered to our load will be defined by this equation. 1/8 times the the absolute value of the maximum amplitude of the voltage squared divided by R sub L, the real component of the load. And really, these are the only two equations that you need to know when considering maximum power transfer. That's really all there is to it, so let's go ahead and just jump right into an example. And this example will also kind of tie up some of the other things that we've talked about in this chapter. So first, let's draw the circuit that we're given. It's got a voltage source with 20 at 0 degrees volts. And that's connected in series with a 5 ohm resistor. And then we've got a 20 ohm resistor there along the parallel line. And then connected to that, we have an inductor, and the impedance is given to us as a phasor already, so that's nice. It's J 3 ohms. And that's connected to a capacitor that has minus J 6 ohms. And all of that is hooked up to our unknown load impedance ZL. And there are two parts of the question. Part A wants us to know, what ZL is needed for max power. Maximum power. Transfer. And we know that already. We just talked about it. We know that ZL for maximum power needs to be equal to the complex conjugate of ZTH, which means really this problem is just about finding ZTH. So let's go ahead and do that. So we see here in our circuit diagram, we've got a 5 ohm resistor, and then we've got this 20 ohm resistor sort of shunting to ground. And so we need to combine these guys first. So we first need to convert it to our Norton equivalent circuit. So we're going to come up with something that looks kind of like this. We need to create our Norton current source. And that'll be connected in parallel with the impedance, which is just 5 ohms. And then that will be connected to the rest of the circuit. And the only part we really care about right now is that 20 ohm resistor in parallel. So I'll just draw that, 20 ohms. And then we'll say we've got the rest of the circuit sort of hanging on there. But we need to know what our current is. I equals something. And so we start with the equation that we've been using forever. Right? I is equal to V over R. So our current is going to be equal to, what did we have? 20 at 0 degrees. 20 at 0 degrees volts over our impedance, which is just 5 ohms. This is going to be really simply just 20 volts over 5 ohms. So our current I here is going to be equal to 4, 0 degrees, amps. So let's come up here and replace that. That's 4 at 0 degrees, amps. All right, then next up, we can combine these impedances in parallel. So let's just go ahead and say, remember our equation here for two impedances in parallel. ZQ is equal to Z1 times Z2 over Z1 plus Z2. And since these are all just resistors, it's much easier. So that's going to be what, 5 and 20. So that's going to be 5 times 20 over 5 plus 20, which is equal to, this is jotted down. Let me punch it into my calculator real quick. 5 times 20 is 100, divided by 25 is 4. Oh, that's kind of embarrassing. I don't think I needed the calculator for that. Okay, 4 ohms. So let's go ahead and redraw our new circuit. We've got our 4 amps. Hanging out in parallel with our 4 ohms, and then we have the rest of the circuit here. J, 2 ohms, and our capacitor at minus J, 6 ohms. And then, of course, what we're looking for, our load impedance, ZL. Okay, so next up is we need to take this and combine it, or convert it back to its Thevenin equivalent circuit. So we're going to have some voltage that we need to calculate in just a second. And that's going to be in series with 4 ohms. And also in series with our J, 2 ohms. And that's going to be connected to our capacitor, connected to our load impedance. And there we go. So we need to figure out what our V is. So we remember that V is equal to I times R. So for us, our V is equal to our I, which was what, 4 amps, times our 4 ohms. Easy enough. That means our voltage V is equal to 16 volts. So we've got 16 volts sitting right there. Now the last thing we need to do, well, not really the last thing, remember that capacitor is minus J6, is we're now ready to combine all of them. So we need to take this guy, convert into it into its Norton equivalent, so that we can combine it in parallel with this resistor. So let's do that. We're going to have some current I in parallel with our resistor and our inductor. And that was 4 ohms, J, 3 ohms, parallel with minus J, 6 ohms, in parallel with our load impedance. All right. So we need to calculate I. We know that I is equal to V over R. So in this case, our I is going to be equal to, what do we have, 16. But now we're over a complex value, so we have to do a little bit more algebra. 4 plus j 3 omega. We're going to get the complexes to the top, so let's multiply by the complex conjugate. 4 minus j 3 omega over 4 minus j 3 omega. And that'll get us what? I is equal to 16 times 4 is 64 minus 16 times 3, so minus j 48, all of that over 4 squared plus 3 squared. Put the rest of that into our calculator. That's going to get us a final answer of 2.56 minus j 1.92 ohms. So there we go, 2.56 minus j 1.92, and it's not in ohms, it's in amps. Amps, cool. Okay. Now we're ready to calculate our Norton equivalent impedance, actually, since we have just these guys in parallel. So we'll go ahead and just call this Zn, and that's going to be equal to the product, so 4 plus j 3 ohms times minus j 6 ohms over 4 plus 3 j ohms minus 6 j 6 ohms. Okay. Now let's multiply everything out. Actually, I'll let you guys do this on your own. I'll skip to the end for the sake of time. When you calculate all of that mess and simplify it, you're going to get a final answer that is Zn is equal to 5.72 minus j 1.68 ohms. And the last thing I want to do here is convert it back to Thevenin. So if I really quickly first draw what we've got that current, which was 2.56 minus j 1.92 amps. In parallel with 5.72 ohms and minus j 1.68 ohms. All of that, remember, is connected in parallel with ZL. Let's go ahead and convert it back to its Thevenin form. So that'll be some voltage source, 5.72 ohms, capacitor minus j 1.68 ohms, then the terminal, then the impedance ZL. Terminal there, I always forget that bottom one. And some V. The last thing we need to do is figure out V, and that'll actually be our VTH. That's I times R, so that's going to be 2.56 minus j 1.92 times the impedance, 5.72 minus j 1.68. And once you FOIL them and simplify, you'll get that our VTH is equal to 11.328 minus j 15.296 volts. So now we've got our whole sort of finished circuit. We also know that our ZTH is equal to 2.56 minus j 1.68 ohms. Oop, not 2.56. Where did I get that from? Oh, that was the current. it come from? So it's 5.72 minus J 1.68. And since if we remember from the very beginning here, what we're looking for, that ZL for maximum power transfer is equal to ZTH conjugated, we'll have that our ZL is equal to 5.72 plus J 1.68. And there we go. There's our impedance for maximum power transfer. And there's a part B here which says, what is Pmax? And remember our equation for that, which is Pmax is equal to 1/8 times the magnitude of VTH squared over R sub L. Let's plug our values in. So Pmax is equal to 1/8 times the square root of VTH. So that's going to be what, 11.328 squared plus 15.296. Also squared. That whole thing squared over the real component of our impedance. So it's going to be over 5.7. So when you punch that in your calculator and simplify, you'll get our final answer here. Pmax is equal to 7.9 watts, the average maximum power transfer. And there we go. That's all there is to it. Really, these problems come down to just being a sort of Thevenin-Morton equivalent circuit problem. Once you know the two sort of basic equations that you've got to start with, which are that ZL is equal to the complex conjugate of ZTH, and that the maximum average power transfer is 1/8 of the absolute value of, or the magnitude of VTH squared over RL. Actually, I realize now I need to change this. VTH. So there you go. That is maximum power transfer. So as always, if you have any questions, comments, concerns, please let me know. And if not, I'll see you guys in the next lesson. Thank you.